Welcome you all. In this session, we are going to discuss in detail about the designing procedure of rotor in induction machine. In induction machine, we know that there are two types of rotor. One is squirrel cage rotor and the second type is slip ring or wound rotor. So now we are going to discuss in detail about how to design squirrel cage rotor. A squirrel cage rotor consists of a laminated core, rotor bars and end rings. The rotor bars and end rings are made of aluminum or copper. The length of rotor is same as that of stator. Some manufacturers keep the length of rotor slightly higher than that of stator in order to utilize the end fluxes. The diameter of rotor is slightly lesser than that of the stator to avoid mechanical friction between the stationary stator and the rotating rotor. So we know that capital D the main dimension. So we know how to calculate the main dimension stator diameter. Now with the help of this the rotor diameter dr is equal to main dimension D stator minus 2 times Lg. Lg represents the length of air gap. So this is all about the diameter of rotor. So in rotor we have some slots. So the number of slots in rotor is chosen in particular fashion. So let us discuss in detail. Proper number of rotor slots are to be selected in relation to the number of stator slots. Otherwise, undesirable effects will be found at the starting of motor. Cogging and carling are two phenomena which are observed due to wrong combination of number of rotor and stator slots. So, while fixing the number of stator slots, we need to consider while fixing the number of rotor slots, we need to consider the stator slots too. In addition, induction motor may develop unprescribable hooks and cups in torque, speed characteristics, or the motor may run with lot of noise. Let us discuss one by one. For selecting the number of slots, the following guidelines are followed. To avoid cogging and carling, the stator slots and rotor slots. So first one is SS is equal to SR, and the second case to avoid carling, SS, that is the stator slots minus rotor slot plus or minus 3P. P is number of poles. To avoid synchronous hooks and cups in torque speed characteristics, plus or minus P, plus or minus 2 times P, plus or minus 5 times P are chosen. To noisy operation, the stator slot minus rotor slot, plus or minus 1, plus or minus 2, plus or minus P, plus or minus 1, plus or minus P, plus or minus 2. These slots numbers are chosen. The next one is the rotor bar current. So the bar current in rotor of squirrel cage induction motor may be determined by comparing the MMF developed in rotor and stator. Hence the current per rotor bar is given by IB is equal to KWS into SS into ZS dash into IR dash, the whole divided by KWR into SR into ZR. So in numerator we have the stator parameters and in denominator we have the rotor parameters. In numerator only parameter with respect to rotor is the rotor current IR dash. So now let us where KWS is the winding factor of stator, S is the number of stator slots, SS dash is number of conductors per slots, stator slots, KWR is winding factor for rotor, SR is number of rotor slots, SR dash is number of conductors per rotor slots, and IR dash is the equivalent rotor current in terms of stator current, and it is given by IR dash is equal to 0.85 IS. This is the relation between the stator and rotor current. Cross-sectional area of rotor bar. Higher current density will lead to reduce the sectional area and hence increased resistance of rotor, copper losses and reduced efficiency. With increased rotor resistance, starting torque will increase. As a guidelines, the rotor bar current density can be assumed between 4 to 7 amps per millimeter square or may be selected from design data handbook. Hence, the cross-sectional area of rotor bar current can be calculated with the help of the current density. We know that the current density should lies between 4 to 7 amps per millimeter square. A value of current density need to be chosen, and with the help of that we can calculate the current. Calculate the cross-sectional area required for the rotor bars. So rotor bars is equal to current divided by del. Okay, so you will be getting the value. Once the cross-sectional area is known, the size of conductor can be selected from the standard table given in data handbook. So once the bar current value is known, if the current value is known, automatically we can calculate the size of conductor. Cross-sectional area if known means the size is also calculated by from the, you can directly take it from the data book. Size and shape of rotor slots. Generally, semi-closed slots or closed slots were very small or narrow openings are employed for rotor slots. In case of fully closed slots, the rotor bars are forced fit into the slots from the sides of rotor. The rotor with closed slots are given better performance to motor in the following ways. As the rotor is closed, the rotor surface is smooth at the air gap and hence the motor draws lower magnetizing current. Reduced noise as the air gap characteristics are better. Increased leakage reactance and reduced starting current. Overload capacity is reduced, undesirable and complex air gap characteristics. Copper loss in rotor bars. Knowing the length of rotor bar and resistance of rotor bar, copper loss in rotor bars can be calculated. Length of rotor bar IB is equal to L plus allowance of for sweeping. Rotor bar resistance is equal to 0.021 times the bar current divided by the bar current area. Copper loss in rotor bars is equal to IB into RB into number of rotor bars. Copper loss in end rings. Mean diameter of end ring is assumed to be 4 to 6 cm lesser than that of a rotor diameter. We know that the main diameter is D and the rotor diameter is lesser than that of the main diameter. Again, the end ring diameter is lesser than 4 to 6 cm lesser than that of the rotor. The mean length of current path in end ring can be calculated. IME is equal to DME. The resistance of end ring can be calculated as RE, which is equal to 0.021 into IME divided by AE, where IME is the mean current path and AE represents the cross-sectional area of end ring. Total copper losses in end rings are 2 times, we have 2 end rings, so 2 times IE square into RE. That's all about the designing parameters of squirrel cage rotor. Thank you.